Section 6.1. The focus of our second semester studies in calculus will be on integration. And the first thing we're going to go over is how to use rectangular approximation to determine area under a curve. And the method we use for that is called finding Riemann sums. To start out, read this problem here. It says a cargo train on a straight track passes through Milwaukee on its way to Chicago at noon. The train, which is traveling at a constant velocity of 16 miles per hour, crosses the border into the Chicago city limits at 5 p.m. How far from Milwaukee is the train? Now, this is really basically an example of a simple problem involving, hold on, let me go back to there, involving distance, rate, and time. We can see clearly here that they give us the rate that the train is traveling at, 16 miles per hour, and it crosses the border at 5 p.m. after coming through Milwaukee at noon, so it's been traveling for 5 hours. So we can just basically say distance equals rate times time, and to find how far from Milwaukee the train is, we would take the rate of 16 miles per hour times time of 5 hours, and we would get 80 miles. Okay, now what does that have to do with integration and Riemann sums? Well, if you look at a graph of a function, in this case it's a constant function. The velocity of the train was constant at 16 miles per hour. That graph would be a horizontal line. On this axis we have time in hours. When I multiply miles per hour times hours, the hours cancel, leaving me with miles. This distance that the train travels can be represented by the area of this rectangle formed between 0 and 5 on the time axis and between 0 and 16 on the velocity axis. So we can see that the base of this rectangle is 5 hours, while the height is 16 miles per hour. And multiplying that gives us the distance, 80 miles. So what we just showed is that if I take a velocity function, I can find distance using the area under the curve. In first semester, I gave you position functions and we used derivatives to find velocity. What we're going to be doing now is kind of going backwards from that, giving you rates and asking you to find values from there. So we can see that answer is 80 miles. Now, on the next page, we have the same kind of a situation. We've got a particle starting at x equals 0 and moving along the x-axis with constant velocity v equals t plus 2. So the difference here is instead of the velocity being constant as it was with the train, the velocity is now dependent on time. Also, instead of a train, it's just a particle moving along the x-axis with a constant velocity. Where is the particle at t equals 3? So, the velocity stays at t plus 2 all the time, so it depends on t. Where is the particle at time 3? Well, again, it started at x equals 0, so its starting point matters. So if I draw an x-axis, and we know that this particle starts at 0 at time 0, okay? And it's moving along the x-axis with a constant velocity. Where is the particle at time 3? Well, again, velocity times time equals distance. So this area under here will give us the distance. Now this isn't a rectangle this time. This time we have a trapezoid. These two sides are parallel and the distance between them is considered the height of the parabola. This is 2 units long, whereas this, let's see, if I plug 3 into the function, 3 plus 2 is 5, so this must be at 5, so the velocity is 5, and this height, the distance between the bases, would be 3 hours. So we can find the area of a trapezoid using the common equation 1/2 base times height, but a trapezoid has two bases that have to be added together. So it's similar to a triangle, the 1/2 base times height. So 1/2, add the bases 2 and 5 together, and then multiply that by the height of 3. And we can find out that that would be 7 times 3 is 21. That would be 10 and 1/2. They didn't give us units, so we have no units. So this area here is 10 and 1/2. That happens to be the distance traveled. So since it started at 2, in those 3 seconds, it moved a total of 10 and 1/2 units, and so now it'll be at 10 and 1/2. So there's our answer. Now, what about this? Now is where we get a problem. Here's where Riemann sums come into play. Let me move this down just a hair here, get my head out of the way. It says a particle starts at x equals 0 again and moves along the x-axis with velocity v of t equals 2t squared plus 2 for time t greater than or equal to 0. So I should start at 0. So at time 0, it starts at 0 again. But this time the velocity is 2t squared plus 2. Where is the particle at time 4? Approximate the area under the curve using 4 rectangles of equal width and heights determined by midpoints. So here's what's going on here. We learned from the last 2 problems that the distance that it's going to travel, okay? The distance this thing is going to travel is velocity times time. But this time, this area that I'm trying to find, all underneath here, is not a recognizable geometric figure, like a rectangle or a trapezoid. I have no idea what the formula is for this type of figure. I don't have an area formula for that. So what I'm going to do is we're going to use what we call rectangular approximation or Riemann sums. Okay? Now, Riemann sums, Riemann is the guy's name who came up with this process. And what we're going to do is we're going to approximate this area kind of a crude way. We're going to use 4 rectangles of equal width. Well, from 0 to 4, if I cut this up into 4 rectangles of equal width, then we'll cut it in half. We'll cut it into 4 sections like this. We're going to use the heights determined by the midpoints. So our first rectangle is going to go between 0 and 1 right here. Okay? And if I draw a rectangle that's as high as the midpoint of that segment, go up from the midpoint, which would be at about a half, well, it would be exactly at a half, and draw a rectangle about that height. We've got a rectangle there. Now there's another rectangle between 1 and 2. So using the midpoint, 1 and a half, go up until you hit the graph. Make your rectangle that high. And there's a second rectangle. The next rectangle would be between 2 and 3. Midpoint being 2 and a half. Use that midpoint to figure out the height and draw your rectangle that high. There's our third rectangle. Our fourth rectangle will have a midpoint at 3 and a half. Go up from 3 and a half until you hit the curve and make a rectangle that high. Now, notice I can find the area of these rectangles really easy just by using base times height. It's hard to find the area of this region under the green curve. It's not going to be an exact, it's an approximation, and like I said, it's kind of crude. This rectangle is too big on the left and leaves a gap on the right. All of these do. Big on the left, gap on the right. Big on the left, gap on the right. But after all is done, hopefully it'll be a close approximation. Each one of these rectangles has a base of 1, but they all have different heights. What was the height of this rectangle? Well, we went up from 1/2, we went up to the curve. So I got to stick 1/2 into the function to find out how high it was. So I'm going to find the volume at a half. So to find this area, what I'm going to do is take they all have a base of 1. Instead of going 1 times this plus 1 times this plus 1 times that plus 1 times that, I'm going to factor out the 1 and find each height. The first height would be the velocity at the first midpoint, 1/2, plus the next height would be the velocity at 1.5. And I don't need that parenthesis. Oh my goodness. Okay, plus, and I didn't need to close it there. Being very foolish here. Let's try this again. So velocity at 1/2 plus the velocity at 1.5, which would be 3/2, plus the velocity at 2.5, which would be 5/2, plus the velocity at 3.5, or 7/2. And that will approximate that area. Okay, so if I go to my calculator, I'm going to go to my calculator and I'm going to type in my y equals menu. I'm going to type in the velocity, which was 2t squared plus 2. And from there, I'm going to go back to my home screen and I'm going to type in that expression. So 1 times, I have the velocity function in y1. So y1 of 1/2, you can use decimals, plus the velocity at 1.5, parentheses will help, close, plus velocity function again at 2.5, plus the velocity at 3.5. And then close my parentheses. Oh, I didn't mean to hit enter. Oh, I'm such a foolish, foolish boy. Well, here, since it's multiplied by 1, I'll just add the last one. I hit enter on accident instead of what I wanted to there. So to that answer, we'll add the velocity at 3.5. So 50. So an estimate is going to be 50 for that particular area. Okay? So I have, where am I here? Oh, let's see here, marker. So the approximate area would be about 50. No units because they don't give any, but that would be the total movement of the particle. So between 0 and 4 and time 4, it'll move from 0 over to 50. It's moving to the right, I know, because the velocity is positive. So remember, when velocity is positive, the object moves to the right 50 units. We can kind of guess that this is about correct. You notice I have a scale of 5 here. This would be 1 times, I don't know, about 3, so maybe that's about 3. This would be 1 times, I don't know, maybe 7-ish, so that's about 7. This would be 1 times about 15-ish, and this would be 1 times about 27 or 28. So 27, 42, 49, 52 would be just an estimate from eyeballing it. Okay, but we have to find the exact velocities. We can't check this, okay? So using the midpoints, I got an area of about 50 square units, okay? Now, I'm going to stop the tape here and start a second video. On the second video, we're going to try to find out, okay, now, what if I wanted you to estimate Riemann approximations using left endpoints and right endpoints? See you then.